So in this talk, I'm very happy to introduce Gao Tian. He is currently a senior software engineer in Microsoft AI framework team and also a Python core dev. And in the next 30 minutes, he's going to introduce us the chaotic locals and how we fix it. Let's have a warm welcome.
Hello everyone, I'm doing a vlog, so could you do me a favor and say hi to the camera? Hi, thank you very much, you're the best. Okay, let's start. So I'm Tian, and I'm currently a Python core dev, working mostly on PDB and tracing related stuff. But today I'm gonna talk about a built-in function that you might have used, locals. Why is it kind of chaos? What are the pitfalls? What problem you can have with locals and how we eventually fixed it? I want to start with a bug. And this bug has some special meanings to me because this is the very first bug I fixed for CPython, which led to my core dev role. And the bug is relatively simple. If we take a look at the code on the left, we have a main function. We do an a = 1, and we set a breakpoint there. And on the right is a set of PDB commands. We print a, it's 1 normal. We do a = 2, and we print a again. Now it's 2. And the problem happens after. We did an LL, which means long list. That basically just shows the source code of the function. And after LL, which seems like innocent, we print a again, and a became 1. And we do an S, which is step. We can step out and let line 4 print a run. That uses the actual local variable, and you can see it also prints 1. So basically, the LL command reverted our changes to the local variable. So what happened? The culprit is actually this function called getSourceLines back in PDB. This is the function to actually retrieve the source lines of a specific object. And there is a check here to check whether if this object is a frame object, whether that is a module level frame. It compares its fglobals with flocals. And when you read object.flocals, it is actually equivalent to call locals in that exact frame, which will revert all the changes to all the changes you've made to that locals dictionary. That sounds a little bit weird, right? Why would they do something like that? So in order to understand why it has that weird behavior, we need to turn the clock back to when the story began. We all know Python has 2 major scopes, global scope and local scope, and they're easy to comprehend. Like global var at module level, that's a global variable, and local var in the function, that's a local variable. Back in 1989, when Guido first developed this language, life was so simple. Both global scope and local scope are just pure dictionary. They are just 2 dicts. So when you access a local variable, that is strictly equivalent to access the dictionary. So basically in the function, when you do locals var = 10, it's exactly the same as locals, which retrieve that local dictionary and then do a bracket local var = 0. So this is a very nice 2-way street. You can just do whatever you want. It changes locals. You can just have the local variable name and change it, read it. It's very nice. But it comes with a cost. If you think about it, with that kind of mechanism, we need to create a new dictionary for each new local scope. And by that, normally we meant function calls. And we can have a lot of function calls in our Python program. Creating a new dictionary takes a while. It's not that slow, but it's definitely, it's a Python object, right? And also it uses more memory. We both know that dictionary is basically a hash map, and a hash map uses more memory than it needs to avoid conflicts. And what's more, when we access the local variable, we need to do a dict read and write every time. So when we do a equals 1, it's quite complicated. It needs to calculate the hash of the variable name. It needs to find the slot. It probably needs to resolve some hash conflict and needs to get the value. We know the dict access is theoretically O1 when everything plays right, but it normally comes with a large constant. So we kind of want to make Python a little bit more performant, especially considering how many function calls are there. That's why we come up with fast locals. So in optimized scopes, and I want to emphasize here, we only change this in optimized scopes where we can determine certain things. And that normally refers to function calls, generators, coroutines, with the exceptions would be like class definitions or the exec function, which will be referred to later. So in those optimized scopes, function calls, we use C arrays instead of a dictionary to store the local variables. So in order to do that, we need to do something at compile time. We need a compiler to figure out how many local variables we actually need by looking at the code. And we create the array in frame. Basically, we generate a frame object when we call a function, and we allocated the exact memory that we need to use because we already know how many local variables are there. So we save some memory and some time because it's just a simple allocation. And instead of using the local variable names as keys to access them, we use indexes. Let's take a quick look at an example here. So we have a very simple function f, a equals 3, b equals 4. And this is the bytecode that we disassembled from this function. And in this bytecode, you can found two bytecode that deals with the local variables, store fast, and at the end you'll see a 0. Of course, there's parentheses saying, okay, this is actually doing it to A, but the 0 is what actually passed into the interpreter, and the bottom one the same, store fast 1. So under the hood, while you do A equals 3 in a optimized scope, what you are actually doing is local, the C array, bracket 0 equals 3, same as B equals 4. So you do not do any dict operations anymore. You do index-based array operation. Well, what about locals? It's still a very nice built-in function that people need to inspect their local variables or do some quick reads. You don't have that anymore because everything is stored in a C array. We can come up with some compensations. Basically, we build up this new function, fast to locals, which converts fast locals to a dict. So what we do is basically, this is a pseudocode. It's not what really is in CPython, but it's the gist. So basically, we keep a single cache-like dictionary for each frame, for each function call. And if it's not there, we create a new one. If it's there, we use that one. And we just grab all the data from the C array and compose that dictionary. Or if it's called second time, update or refresh or refill that dictionary. And frame.f locals, which is less frequently used, it is basically the same as locals. With that, as you can realize, accessing local variables is not equivalent to accessing the dictionary anymore, because when you do local var equals 10, you are changing the local variable under the hood in the C array. But when you do locals bracket local var, you are just changing that cache dictionary. It has no impact on the underlying local variables. So it's not a two-way street anymore. That's probably not too bad. What could go wrong, right? Let's just remind ourselves of some facts. Locals or frame.locals, they will always return the same dictionary if they're called in the same frame or in the same function call. As I said, it's the same cache. We will not create a new dictionary. And it will refill the dict with the current local variables. So it refreshes it for every call. Then let's take a look at this example, right? It's a simple function. We do an x equals 0 in the beginning, and then we call it locals and assign that to current locals. After that, we change the value of x to 1, and we do another locals and store it to after locals. Very simple, right? And what is current locals bracket x? What's the value of that? Well, it's 1. It's 1. Even though we assigned local, we called locals assigned to current locals before we change the value of x to 1, current locals x is still 1, because remember, the two locals returns the same dictionary. So as you can tell, current locals is after locals. They're the same dictionary, and every call to locals will refill that dictionary. So current locals is implicitly changed during the second locals call. And also, exec could have an expected result. We also have two examples there. And remember, exec is one of the exceptions where the local scope is literally a dictionary. So we have two very similar functions. The top one has an x equals 0, which is not used, kind of not used. And we do an exec x equals 1, and then we print locals. On bottom, we do not have the x equals 0. We exec the same statement and we print locals after it. What are the results? Well, the first one, x is 0, and the second one, x is 1. So even though x equals 0 is kind of used or not, but the result of the two functions are different and somewhat unexpected. Why? Because exec without extra argument for globals and locals will implicitly call locals and use that as its local namespace, which is, well, kind of corrected behavior. And when it does that, so if you take like the first function, it implicitly called locals and execute x equals 1, so that dictionary is filled with x1. But when you call locals again in the print function, it will refill that exact same dictionary with the value of all local variables. And in the top function, x is a local variable, so it will fill it with x0. On the contrary, in the bottom one, x is not a local variable, so exec fills the dictionary returned by locals with x1, and the second locals did not refill anything. It's the same dictionary, it's already refilled, but it's not updated because x is not a local variable anymore, so it returns x is 1. Actually, there are some exceptions. Or there are some other ways to use this thing. Well, we have a very similar function on the top, like x equals 0, x equals 1, and we print x, and we know it's 0 because locals is the dictionary. The locals dictionary is refilled with the local variable. But if we do it kind of differently, we call locals once. We store that in a variable ns, meaning namespace, and we explicitly pass that namespace to exec. We will have I don't know if this is expected or not, we will have a different behavior, a different result. That is because x equals 1 did fill x1 to the namespace, and because we did not call locals again, it's not refreshed, so x equals 1 is passed to the next exec function, and so print x prints 1. So with this example, basically what we know is that, well, you can use locals as a namespace to kind of pass data around, just don't read it again. So let's go back to the bug at the very beginning. What happened? When we do a equals 2, we're basically doing an exec with the frames global and locals. And when we print a, that's okay, it basically prints it out. But when we do LL, we read the F locals, or that is equivalent to calling locals in that frame, which refills that exact same namespace with the actual current local variable value, and a is 1, So this LL implicitly reverted our changes to the local namespace, and then we print A. When we print A again, it's gonna be 1. Wait, something is off. So basically, you are saying that any changes to the locals dictionary cannot be passed to local variables, to the actual local variables, because I know that's wrong. You're lying? How could it ever work with debugger? Because I've used PDB before and I know the value can be changed. If we take a look at the right, if we take a look at the code on the right, we at a breakpoint, we do an A equals 2, quick and simple, and we do a next. Basically, we let print A run, and print A did print 2, which proves the local variable A got correctly changed. So that contradicts what you said, right? To make it work, we kind of have this special treatment. Basically, we have fast to locals brother, locals to fast, which converts the local variables back to fast variables. So we have that same dictionary, right? And we just pick everything in it and see if there is a corresponding fast variable, and we refill the C array to make sure the debugger kind of work. And this function is implicitly called right after each trace callback. So basically, when you do a step or next function in PDB, it goes out of the trace callback and it runs this locals to fast to store whatever you changed to the locals variable. So if you consider it from a debugger's view, PDB, in order to change local variables, PDB needs to store the locals dict of the frame. So use it as a cache because we do not want to read it again. So we store that as a single, as a namespace in PDB, and we execute statement with that cached version of dict because we can only use that if we cannot call locals to get that dict again. And we need to make sure that no extra read is performed after we write to it because that will revert whatever we changed. And the last thing is that we can wait for the locals to fast to write it back, and then everything is great. Well, it sounds a little bit complicated, and PDB failed to do it. It's just too difficult. There are unsolved bugs in PDB. For example, if you switch frames using up or down, it will erase your changes because that will read the locals again. And of course, if you think about it, if the user can always explicitly call frame.f locals, and there's nothing you can prevent from it, right? They can just do it and erase all the changes. That's kind of bad. So to summarize, we want to summarize the thing. You can't change local variables through locals, unless in the trace callback. And changes to locals will be reverted on the next call of locals, unless what's modified is not a local variable. And you can't really pass around data with exec, unless with an explicit namespace. It's a chaos. So we need to make it better. And we have a clear direction, right? First of all, we want to minimize the number of applications to break. If there's one thing that I learned from developing CPython is backward compatibility is important. We do not want to break millions of users' applications. So that's the most important thing. And then we want to clarify the semantics of locals and frame.f locals because, I've explained more than 15 minutes of what it does to you, and you are probably still very confused. That's because it does not have a clear semantics. No one can explain that well. And but that's not our only goal because we can make it really simple but not working, right? We also need to empower users to accomplish their goals. Like we can't make PDB work properly. We can't, and we cannot also afford to make local simple but make PDB still not working. That's not good. We want to do that. So all in all, less surprise, less implicity. And that's why that's how we came up with PEP 667. And it's authored by Mark Shannon, sitting over there, and myself. And most credits should go to Mark because he did the design and I only did the implementation. The implementation is trivial, even I can do it. Basically, in that tab, we split the semantics into two distinct operations. So locals, still in the optimized scope, I want to emphasize there, it will always return a dict snapshot. A dict snapshot is basically all the local variables and their corresponding value at that exact moment. And after that, that dictionary is just a dictionary. It has no magic whatsoever. So you can never change local variables through that dictionary in any case. And also, every call to locals will return a different dictionary, a new dictionary. So you don't have any implicit behaviors. But that does not help with the debugger, right? So we changed frame.flocals to something that we specifically use for debugger. So instead of like a dictionary, we let it returns a write-through proxy, which is still a mapping. You can still kind of use it like a dictionary. You still get item and set item and everything. But now it's transparent. All the changes made to it are effective immediately. So basically, if you do frame.flocals bracket x equals 1, the underlying local variable x will be assigned to 1 immediately so that you can use it in the debugger and do not need to worry about, well, if it's going to be reverted. So what's changed? There are some examples that we gave before, that's on the left. And after that, as you can see, when we print locals, it will print an empty dictionary because there is no local variable in that function, period. There is no local variable. So, well, locals will print an empty dictionary. And at the next one, well, there is a local variable, and the local variable has a value 0, so it will print x0. Another example we gave before. So current locals, after calling locals, will be assigned to a dictionary x0, and it will never be implicitly changed after. The next call to locals will return a new dictionary instead of like changing the existing one. So current locals is not after locals anymore, and current locals x is 0, which is much more expected. And we can take a look at some new things it brings in. We get the frame by sys.getFrame, this is the current frame, and we do add frame.flocals x equals 1. Before PEP 67, the print x will print 0 because flocals is just locals. It's a dictionary, and changing the value of the dictionary has no impact to the underlying local variables. But after that, print x will print 1 because, well, now it's a write-through proxy. When you change that, the underlying variable is also changed. And this is something that's even more interesting, especially to the debugger. We can actually pass this flocals to the exec function because exec takes an arbitrary mapping. And as you can tell, if we exec x equals 1 with an explicit flocals, before, it's still 0 because flocals is dictionary, obviously. But after that, x equals to 1, that statement will write to that local namespace flocals, and because that's a write-through proxy, it will change the underlying local variable x. So print x will give you 1. So that's how debugger can work with this new set of interface. It can easily execute arbitrary statements and change the local variables. So with this new interface or new PEP, debuggers do not need to rely on locals too fast anymore. And actually, we no-opt it, so it's still there. We do not want to break people's code, but it does not do anything anymore. And all the changes to local variables through flocals are immediate, which means we do not need to cache the locals dict. We also do not need to worry about accidentally reading locals. You can read it whenever you want, and you can write to it whenever you want. Thank you very much, and I can take some questions.
I just want to say Tian's being far too modest, and he deserves most of the credit. And now an actual question.
That's Mark Shannon, the author of that.
So why didn't you make locals return the write-through dict like flocals? Why doesn't flocals in the frame and the locals function just return the same thing?
Great question. We thought about that because we still want locals to return a dict. So there's no write-through dict, right? It's either a new object that is write-through or it's a dict. So locals are much more used by intermediate users to just inspect stuff. And sometimes their code kind of assumes it's a dictionary and do a lot of dictionary-specific stuff on that. And frame.f locals, because you need to get the frame object first, and it's more advanced, and it's mostly used by debuggers. So that's how we split the semantics. The locals, easier one, just keep its type and do nothing surprising, and f locals making it more powerful. Okay, that's everything. Thank you all. If you have more questions, feel free to ask me after this. Thank you.
Now a warm applause for Tian. Great presentation. Then that's the end of this session. The next session will be 5 p.m.
Sorry. Do you have another question?
Yeah. I was just running. You mentioned that one of the metrics for success is how many projects you broke.
Mm-hmm.
But how do you know how many projects you broke?
Well, you'll hear complaints. but yeah, we definitely take a look at locals, and we search a little bit on how normally debuggers using frame.f locals, because it's not fully backward compatible. If it's fully backward compatible, we will change nothing, right? That's fully backward compatible. So we need some new mechanism, and we know that we will probably break something, but for debugger developers, they should know this well enough to adapt to it, and it's definitely not difficult to do it. And but for normal users, locals kind of behaves the same without some implicit weird behaviors. So if they rely on that, their code is probably kind of wrong anyway.
I see. Thanks.
Any other questions?
So it seems like the compiler would know if the function is going to call locals, just inspection. Did you consider not doing an optimized frame when the compiler sees that locals is being called?
The compiler does not know that because you can pass local in as a dynamic variable.
Fair. Okay.